take a look at the system of linear equations. L1 x plus m1 y is equal to P, and L2 x plus m2 y is equal to Q. This system of equations can have a unique solution, no solution, or infinitely many solutions. Let's discuss the case when the system has a unique solution. The given system of linear equations will have a unique solution if L1 upon L2 is not equal to M1 upon M2. That is, if L1 into M2 minus L2 into M1 is not equal to 0, then the system will have a unique solution. You have learnt that a given system of linear equations can be expressed in the form of a matrix. So, on representing the given system in the form of a matrix, we obtain the equation shown. Let us now see how we can define a unique solution of a linear system in terms of a matrix. Consider the 2 by 2 matrix with the elements L1 and M1 in the first row, and L2 and M2 in the second row. The real number L1 into M2 minus L2 into M1, which is associated with the matrix, can be obtained by multiplying the diagonal elements and then subtracting the products. This real number is known as the determinant of the 2 by 2 matrix. Let us now define determinants in terms of functions. Let A be a set of square matrices and B be a set of real or complex numbers. Also, let f be a function from A to B, defined by f of x is equal to b, such that x belongs to A and b belongs to b. Then f of x is called the determinant of x. Determinant of A is denoted as det of A or delta. A determinant can also be defined as a function whose domain is a set of all square matrices and codomain is the set of the union of real and complex numbers. If A is any square matrix, then determinant of A is denoted as shown. Note that determinant of A is not modulus of A, as a modulus exists only for real numbers. Also note that determinants exist only for square matrices. Moving forward, let us learn to evaluate the determinant of a matrix with real entries up to order 3, beginning with the determinant of a matrix of order 1. Consider a 1 by 1 matrix A. The determinant of matrix A is A11. Observe that the determinant of a matrix of order 1 is the entry in the matrix itself. Next, we have the determinant of a matrix of order 2. This we have already discussed. In this case, det A is equal to A11 into A22 minus A12 into A21. Lastly, we have determinant of a matrix of order 3. Consider the general form of a 3 by 3 matrix. The determinant of a third order matrix can be determined by expanding it along a row or a column in terms of a second order determinant. This is known as the expansion of a determinant. The determinant of matrix A can be calculated in 6 ways as shown. Let's discuss each case one by one. First, let us learn to expand the determinant along the first row. Beginning with the first step, multiply the first element, A11 of the first row, by minus 1 raised to the power of 1 plus 1, where 1 plus 1 is the sum of the suffixes of A11. And then, by the second order determinant, obtained by deleting the elements of the first row and the first column of matrix A. This is because A11 lies in the first row and the first column. Hence the product corresponding to the above step is as shown. In step 2, we multiply the second element A12 of the first row by minus 1 raised to the power of 1 plus 2, where 1 plus 2 is the sum of the suffixes of A12. And then, by the second order determinant obtained by deleting the elements of the first row and the second column of matrix A. This is because A12 is an entry in the first row and the second column. The product is as shown. In step 3, we multiply the third element A13 of the first row by minus 1 raised to the power of 1 plus 3, where 1 plus 3 is the sum of the suffixes of A13. And then, by the second order determinant obtained by deleting the elements of the first row and the third column of matrix A. This is because A13 lies in the first row and the third column. The product is as shown. Lastly, we add the results of the three steps to get the determinant of A. The determinant of A is as shown. On simplification, we get the required determinant of matrix A. Let us now apply these steps to expand the determinant of A' along the first row. The first entry of the first row is 2. Multiplying it with minus 1 raised to the power of 1 plus 1, where 1 plus 1 is the sum of the suffixes of A11, which is the position of this entry in the matrix, and then by the second order determinant obtained by deleting the elements of the first row and the first column of the determinant. Similarly, the other two terms can be obtained. On simplifying, we get determinant of A' is equal to minus 37. Similarly, the determinant can be expanded along the second row by the same method. This is the required determinant of A. Let us now find determinant of A' again by expanding it along the second row to understand the concept better. The first entry in the second row is 1. Multiplying it with minus 1 raised to the power of 2 plus 1, where 2 plus 1 is the sum of the suffixes of A21, which is the position of this entry in the matrix, and then by the second order determinant obtained by deleting the elements of the second row and the first column of the determinant. Similarly, the other two terms can be obtained. On simplifying, we get determinant of A dash is equal to minus 37. Observe that the determinant of A dash, when calculated along the first row or the second row, is the same. In general, we can say that calculating the determinant of A dash in any one of the 6 ways yields the same result. Let us now see the remaining 4 ways in which a determinant can be expanded. Following the same 4 steps, determinant of A can be found on expanding it along the third row, as shown. The required determinant of A is as shown. In a similar manner, the determinant of matrix A can be expanded along each column. Observe that the value of the determinant of matrix A yields the same result when evaluated along rows R1, R2, and R3, and along column C1. Similarly, the determinant of A will be the same along columns C2 and C3. In this way, the determinant of a square matrix can be found along the rows or along the columns. Some important points to be kept in mind while finding the determinant of a square matrix are: if any row or column contains maximum number of zeros, then finding the determinant along that row or column makes the calculation easier. If all the elements of a row or a column are zeros, then the determinant of that matrix is 0. If M and N are 2 square matrices such that M is equal to K into N, where K is a real number, then the determinant of M is equal to K raised to the power of N into determinant of N, where N is the order of matrices M and N. At the time of expansion, the ijth term can be multiplied by +1 or -1, depending upon whether I plus j is even or odd, instead of multiplying it by -1 raised to the power of I plus j. We will discuss some of these properties in the coming modules. Let A be any 2 by 2 square matrix. From our previous knowledge, the determinant of A can be evaluated, which is quite simple. However, evaluating the determinant of a third-order square matrix is a bit complex and a lengthy process, as there are so many terms to be multiplied and then simplified. However, by using some properties of determinants, we can obtain the maximum number of zeros in a row or a column in a determinant which simplifies the evaluation. Let us learn these properties one by one. The first property is the determinant of a matrix is equal to the determinant of the matrix obtained by interchanging its rows and columns. In other words, the value of a determinant remains unchanged if its rows and columns are interchanged. Let A be 3 by 3 square matrix. Let's evaluate the determinant of A. By expanding it along the first row, we get A1 times of B2 C3 minus B3 C2 minus A2 times of B1 C3 minus B3 C1 plus A3 times of B1 C2 minus B2 C1. Now, let B be the matrix obtained by interchanging the rows and columns of matrix A. To verify the property, we have to show that on expanding determinant B along any row or column, we get the same value as we get on expanding determinant A. So, let's expand determinant B along the first column. Observe that we get the same value as we get on expanding determinant A. Hence, we have determinant of A is equal to determinant of B, and matrix B is nothing but transpose of matrix A. Thus, the determinant of square matrix A is equal to the determinant of its transpose. Let's consider an example to verify the property. Let A be a 3 by 3 square matrix as shown. On evaluating determinant A along the first row, we get it equal to -1. Now, A transpose can be obtained by interchanging the rows and columns of matrix A. Evaluating determinant of A transpose along the first column, we get its value equal to -1, which is the value of determinant A. Hence, the determinant of matrix A is equal to the determinant of its transpose. In a determinant, the ith row is denoted by R with subscript I. Similarly, the ith column is denoted by C with subscript I. Mathematically, an interchange of the rows and columns in a matrix is denoted as shown. Let's now move on to the next property. It says that the sign of the determinant of a square matrix changes if any two rows or columns in the matrix are interchanged. Consider a 3 by 3 square matrix A. Let's evaluate the determinant of matrix A. By expanding it along the first row, we get A1 times of B2 C3 minus B3 C2 minus A2 times of B1 C3 minus B3 C1 plus A3 times of B1 C2 minus B2 C1. Now, let B be the matrix obtained by interchanging the first two rows of matrix A. To verify the property, we have to show that the determinant of matrix B is the negative of the determinant of matrix A. So, let's expand determinant B along the second row. we get minus of A1 times of B2C3 minus B3C2 plus A2 times of B1C3 minus B3C1 minus of A3 times of B1C2 minus B2C1. Observe that this is the expansion of the minus of determinant A. Thus, we have determinant of B is equal to minus of determinant of A. Hence, we can say that a determinant changes its sign when two rows or columns are interchanged. This verifies the property. Let us now verify it by taking an example. Let A be a 3 by 3 square matrix as shown. On evaluating determinant A along the first row, we get its value equal to minus 1. Let B be the matrix obtained on interchanging rows R1 and R2 of matrix A. On evaluating determinant B along the first row, we get 1, which is equal to minus of determinant A. Hence, the determinant of matrix B is equal to the minus of the determinant of matrix A. Moving on to the next property. It says that if any two rows or columns of a square matrix are identical, then the value of its determinant is 0. Let us consider a matrix A, in which the elements of the first row and the second row are identical. Expanding the determinant of matrix A along the first row, we get A1 times of A2 B3 minus A3 B2 minus A2 times of A1 B3 minus A3 B1 plus A3 times of A1 B2 minus A2 B1. On simplifying, we get the determinant of matrix A is equal to 0. Similarly, the determinant of matrix A is 0 if any two columns are equal. Hence, if any two rows or columns of a square matrix are identical, its determinant is 0. Let us now verify it by taking an example. Let A be a 3 by 3 square matrix such that its first and second columns are the same. On evaluating determinant A along the first row, we get zero. Hence, the determinant of a matrix, when two of its rows or columns are identical, is 0. This verifies the result. You learned 3 properties of determinants in the first part of this lesson, which simplify evaluation by obtaining the maximum number of zeros in a row or a column. Now, let us learn some more properties of determinants. The fourth property says that if all the elements of a row or a column of a square matrix are multiplied by a number, k, then the value of the determinant of the matrix obtained is k times the determinant of the given matrix. Let A be a 3 by 3 square matrix as shown. On expanding along the first row, determinant A is equal to A1 times of B2 C3 minus B3 C2 minus A2 times of B1 C3 minus B3 C1 plus A3 times of B1 C2 minus B2 C1. Now, let B be the matrix obtained by multiplying each element of the first row by a constant k. Expanding B along the first row, we get k into A1 times of B2 C3 minus B3 C2 minus k into A2 times of B1 C3 minus B3 C1 plus k into A3 times of B1 C2 minus B2 C1. Taking k common, we have determinant of matrix B is equal to k times determinant of matrix A. This verifies the property. By this property, we can take out any common factor from any one row or any one column of a given determinant. Two results can be deduced from this property. The first is that if the elements of a row or a column of a square matrix are k times the elements of another row or column, that is, if two rows or columns of a determinant are proportional, then the value of its determinant is 0. Let's verify this result with an example. Consider determinant A, such that its second and third rows are proportional. Here, each element of the third row is 2 times the corresponding elements of the second row. Now, from property 4, on taking 2 common, determinant A can be written as 2 times the determinant whose second and third rows are identical. And from property 3, we know that if 2 rows or columns of a square matrix are identical, then the value of the determinant is equal to 0. Hence, the determinant of A is equal to 0. This verifies the result. The next result is that if M and N are 2 square matrices such that M is equal to K into N, where K is a real number, then the determinant of M is equal to K raised to the power of N into the determinant of N, where N is the order of matrices M and N. Let us apply this result to a matrix M. It can be written as 2 matrix N, where N is a matrix with the entries 5, 1 in the first row and 3, 4 in the second row. On evaluating, determinant M is equal to 68. And on evaluating determinant of N, we get 17. Observe that determinant M is equal to 2 square into determinant N. This verifies the result. Moving on to property 5. It says, if the elements of a row or a column of the determinant of a matrix are expressed as the sum of two or more terms, then the determinant can be expressed as the sum of two or more determinants. Suppose the elements in the first column of a determinant are expressed as the sum of two terms. Let's show the determinant can be expressed as the sum of two determinants. Consider the left-hand side. Expanding the determinant along the first column, we get A1 plus L1 times of B2C3 minus B3C2 minus of A2 plus L2 times B1C3 minus B3C1 plus A3 plus L3 times B1C2 minus B2C1. On simplifying, it can be written as shown here. Observe that the first three terms of the expansion of the first determinant along the first column and the last three terms are the expansion of the second determinant along the first column. This is the required right-hand side. Note that similar results can be obtained by considering the other rows and columns. For example, consider the 2 by 2 matrix shown here. Its determinant is equal to AD minus BC. Now, let's find the determinant by writing it as the sum of two determinants. Using property 4, take minus 1 common from the second row of the first determinant. Now, the first determinant has two identical rows. So its value is 0, and the value of the second determinant is equal to AD minus CB. Hence, the value of the determinant is equal to AD minus BC. This shows that the value of the determinant is the same as the value of the determinant when it is expressed as the sum of the two determinants. Moving on to the last property. It says, if the elements of a row or column of a square matrix are added with k times the corresponding elements of another row or column, then the value of the determinant of the given matrix does not change. That is, the value of a determinant remains unchanged if we apply the operation Ri goes to Ri plus k times Rj, or Ci goes to Ci plus k times Cj. For example, if we apply the operation C1 goes to C1 plus k into C2 to matrix A, the resultant determinant of matrix B has the same value as that of determinant A. Let's verify it by expanding the resultant determinant B. Take a look at determinant B. Observe that the elements in the first column are the sum of two terms. By property 5, we know that if the elements of a row or a column of a determinant are expressed as the sum of two or more terms, then it can be expressed as the sum of two or more determinants. Hence, determinant B can be expressed as the sum of two determinants. In the second determinant, each element of the first column is multiplied by k. By property 4, we can take k outside the determinant, which will not change its value. Now, we have determinant A plus k times a determinant whose first and second columns are identical. By property 3, we know that If two rows or columns of a determinant are identical, then its value is equal to 0. Thus, we have determinant B is equal to determinant A, and hence the result. Note that similar results can be obtained by considering the other rows and columns. Let us consider an example now. Without using property 6, the value of delta on evaluating comes to 0. Let us now apply property 6 to this determinant and verify that in both the cases, the result is the same. Applying column operation C1 goes to C1 minus 6 times C3. We get the determinant with its first two columns having the same entries. Now, by property 3, if two rows or columns of a determinant are identical, then its value is 0. Observe that either way, the result is the same. But with the help of properties of determinants, it can be simplified more easily. Given a triangle ABC, with vertices having the coordinates x1, y1, x2, y2, and x3, y3. How do you determine its area? Yes, you are right. Its area can be determined by substituting the coordinates of the vertices in the formula half of x1 times of y2 minus y3 plus x2 times of y3 minus y1 plus x3 times of y1 minus y2, which is the formula to calculate the area of a triangle when its three vertices are given. Now, observe the expression inside the square bracket. Let's see if it can be expressed in the form of a determinant. Consider the determinant with the first column having the x-coordinates of the vertices of the given triangle, the second column having the y-coordinates of the vertices, and the third column having all ones. On expanding this determinant along the first column, we get x1 times of y2 minus y3 plus x2 times of y3 minus y1 plus x3 times of y1 minus y2. Observe that this is the same expression as we had in the formula to calculate the area of a triangle. So replacing this expression by the determinant in the formula, we get a new formula to calculate the area of a triangle in terms of a determinant. Let's use this formula to calculate the area of the triangle when its three vertices are -2, 3, 4, 4, and 2, -3. In terms of a determinant, the area of the triangle formed by the given vertices can be written as shown. On expanding the determinant along the first column, we get the following. On simplifying, we get -20. This means the area of the triangle is negative, which is not possible. Hence, while calculating the area of a triangle by using this formula, we need to take the absolute value of the determinant to avoid negative values, if any. This implies area of the triangle is equal to 20. Hence, the area of the triangle is 20 square units. If the area of a triangle is given and you have to calculate an unknown coordinate, then use both the positive and the negative values of the determinant for the calculation. What do you think will be the area of the triangle formed by 3 collinear points? Let's see. Substituting the vertices in the formula, we get the determinant as shown. Now, taking 2 common from the first column, we get half into 2 times the determinant having the first and the third columns the same. Recall that if 2 rows or columns of a square matrix are identical, then the value of the determinant is 0. This implies the value of the determinant is 0, and hence the area of the triangle is 0. It can be verified graphically also by plotting these points. Observe that no triangle is formed with the given points, and hence the area is equal to 0. This leads us to the result that the area of a triangle formed by 3 collinear points is equal to 0. Consider the determinant of a 3 by 3 square matrix. A. It can be determined by expressing it in terms of a second-order determinant. So far, you have learned that the expansion of a determinant of order 3 can be done in 6 ways, each corresponding to the 3 rows and the 3 columns. Here, the expansion of the determinant is along the first row. Observe the first term of the right-hand side of the expression. It is obtained by multiplying the first element, A11, of the first row by -1, whole raised to the power of 1 plus 1, where 1 plus 1 is the sum of the suffixes of A11 and the second-order determinant obtained by deleting the elements of the first row and the first column of matrix A. This second-order determinant obtained by deleting the elements of the first row and the first column of matrix A is known as the minor of A11. Mathematically, the minor of an element Aij, the determinant of a matrix A, can be obtained by finding the determinant of the matrix obtained by deleting the ith row and the jth column. The minor of an element Aij is denoted by Mij. Similarly, the minor of A12 can be obtained by finding the determinant of the matrix obtained by deleting the first row and the second column. And the minor of A13 is the determinant of the matrix obtained by deleting the first row and the third column. In the same way, the minor of the other elements of matrix A can be found. Now, let's get back to the expansion of determinant of A along the first row. In terms of minors, determinant of A can be written as shown. From this discussion, we conclude that the determinant of A is equal to the sum of the product of each element of a row or a column with its corresponding minors and -1 whole raised to the power of the sum of the suffixes. Also, it is clear that the minor of any element of determinant A is a determinant of order 2. This leads us to the result that the order of minor of an element of a determinant is 1 less than the order of the determinant. Let's observe the expansion of determinant of A along the first row in terms of minors again carefully. The minor of A11 together with minus 1 whole raised to the power of 1 plus 1 is known as the cofactor of A11. Similarly, the minor of A12 together with minus 1 whole raised to the power of 1 plus 2 is known as the cofactor of A12. And the minor of A13 together with minus 1 whole raised to the power of 1 plus 3 is known as the cofactor of A13. Let's now define cofactors in mathematical terms. Let Aij be an element in the ith row and the jth column of a square matrix A. The product of minus 1 whole raised to the power of I plus j and the minor of Aij is called the cofactor of Aij. The cofactor of the element Aij is denoted by capital Aij. So, in terms of cofactors, the expansion of the determinant of A can be written as the sum of the products of the elements of the first row with their corresponding cofactors. Similarly, the determinant of A can be calculated in 5 other ways, that is, along the second row, third row, first column, second column, and the third column. This discussion leads us to a result that the determinant of a matrix is equal to the sum of the products of the elements of any row or column with their corresponding cofactors. Let's find the determinant of A along the second column by finding the cofactors. The minor of the first element of the second column is the determinant of the matrix obtained by deleting the first row and the second column. Similarly, the minor of the second and the third element of the second column can be determined. Now, the cofactor of the element A12 is equal to the product of minus 1 whole raised to the power of 1 plus 2 and its minor. Similarly, the cofactor of A22 and A32 can be obtained, which are as shown. Now, as per the definition, the determinant of matrix A is equal to the sum of the products of the elements of the second column with their corresponding cofactors. Substituting the values, and then simplifying, we get the determinant of A as shown. Note that if the elements of a row or column are multiplied with the cofactors of any other row or column, then their sum is 0. Consider a 3 by 3 matrix A as shown. Let's verify the result by showing that the sum of the products of the elements of the first row with the cofactors of the corresponding elements of the second row is 0. The minor of the first element of the second row is the determinant of the matrix obtained by deleting the first column and the second row. This is equal to 10. Similarly, the minor of the second element of the second row is equal to minus 13, and the minor of the third element of the second row is equal to minus 4. Now, the cofactor of the element A21 is equal to the product of minus 1 whole raised to the power of 2 plus 1 and its minor. Hence, the cofactor of the element A21 is equal to minus 10. Similarly, the cofactors of A22 and A23 can be obtained, which are as shown. Now, let's evaluate the sum of the products of the elements of the first row with the cofactors of the corresponding elements of the second row. On substituting the values, we get 0, Hence, if the elements of a row or column are multiplied by the cofactors of any other row or column, then their sum is 0. In matrices, you learnt to find the inverse of a square matrix by using elementary row or column operations. If A is a square matrix such that A inverse exists, then to find A inverse using elementary row or column operations, we write A is equal to I into A or A into I, and apply a sequence of elementary row or column operations till we get I is equal to B into A or A into B. In each case, matrix B will be the inverse of matrix A. In addition to the method discussed now, there is another method that is quite frequently used to find the inverse of a square matrix. Before learning this method, let's learn what the adjoint of a matrix is and some important theorems based on it. Consider a 3x3 square matrix A. Let Aij denote the cofactor of the element Aij of matrix A. On replacing the elements of the given matrix A by their corresponding cofactors, we get the matrix shown here. The transpose of this new matrix is known as the adjoint of the given matrix A. Hence, the transpose of the matrix obtained by replacing the elements of a square matrix A by the corresponding cofactors is called the adjoint of matrix A. It is denoted as shown. Now, let us see how we find the adjoint of a 2x2 square matrix, shown here. First, we find the cofactors of the elements of matrix A, which are as shown. Now, as per the definition, the transpose of the matrix obtained by replacing the elements of a square matrix by the corresponding cofactors is the adjoint of that matrix. So, the adjoint matrix has D and minus B in the first row and minus C and A in the second row. The adjoint of a 2x2 square matrix can be obtained by interchanging A and D and by changing the signs of B and C. Let us now prove an important theorem on the adjoint of a matrix. The theorem states that if A is any given square matrix of order n, then A into adjoint of A is equal to adjoint of A into A, which is equal to determinant of A into I, where I is the identity matrix of order n. Let A be a 3x3 square matrix, as shown here. By definition, adjoint of A is the transpose of matrix A obtained by replacing the elements of the square matrix A by the corresponding cofactors. Now, let us find the product of matrix A and its adjoint. The resultant matrix is as shown. This is equal to a diagonal matrix with each diagonal element equal to the determinant of A. This is because the sum of the product of the elements of a row or a column with the corresponding cofactors of another row or column of a square matrix is 0. Now, taking determinant of A common, we get determinant of A into I, where I is a 3x3 identity matrix. Hence, A into adjoint of A is equal to the determinant of A into the identity matrix. Similarly, we can prove that the adjoint of A into A is equal to the determinant of A into the identity matrix. Hence, the result is true for any given square matrix of order n. While calculating determinant of a matrix A, you often come across situations when it comes equal to 0. A matrix whose determinant is equal to 0 is said to be a singular matrix. Mathematically, a square matrix is said to be singular if its determinant is 0. So, here we can say that A is a singular matrix. On the contrary, a square matrix is said to be non-singular if its determinant is not equal to 0. For example here, the determinant of A is -2, which is not equal to 0. Hence, A is non-singular. Let's now learn a theorem which says that if A and B are non-singular matrices of the same order, then AB and BA are also non-singular matrices of the same order. To prove this result, let us consider two non-singular matrices A and B of order 2 by 2 as shown. Observe that A into B is a square matrix of order 2 by 2, and its determinant is not equal to 0. Also, B into A is a square matrix of order 2 by 2, and its determinant is also not equal to 0. This shows that A into B and B into A are non-singular matrices of the same order as that of A and B. Next, we claim that the determinant of the product of matrices is equal to the product of their respective determinants. That is, determinant of A into B is equal to determinant of A into determinant of B. Consider the same matrices A and B. The determinant of A is equal to 16, and the determinant of B is equal to -6. So, determinant of A into determinant of B is equal to -96. And the determinant of A into B, as we calculated earlier, is equal to -96. This shows that determinant of A into determinant of B is equal to determinant of A into B. This leads us to a theorem which states that the determinant of the product of matrices is equal to the product of their respective determinants. That is, determinant of A into B is equal to determinant of A into determinant of B, where A and B are square matrices of the same order. Let's now move on to the next theorem, which states that if A is a square matrix of order n, then the determinant of adjoint of A is equal to determinant A raised to the power of n minus 1. Let's begin with the proof. In the previous theorem, we proved that A into adjoint of A is equal to determinant of A into the identity matrix. This implies that the determinant of A into adjoint of A is equal to determinant of A into the identity matrix. Now, recall the result that if M and N are two square matrices such that M is equal to K into N, where K is a real number, then the determinant of M is equal to K raised to the power of N into the determinant of N, where N is the order of the matrices M and N. Using this result, we have determinant of A into adjoint of A is equal to determinant of A raised to the power N into the identity matrix. Also, the determinant of the product of matrices is equal to the product of their respective determinants. So we further have determinant of A into determinant of adjoint of A is equal to determinant of A raised to the power N into determinant of the identity matrix. Now, the determinant of the identity matrix is equal to 1. This implies that determinant of A into determinant of adjoint of A is equal to determinant of A raised to the power N. On dividing both the sides by determinant of A, we get determinant of adjoint of A is equal to determinant of A raised to the power of N minus 1. Hence the result. Consider two matrices A and B shown here. On evaluating the product of matrices A and B, we get an identity matrix. That means matrix B is the inverse of matrix A, and vice versa. Such a matrix A is said to be an invertible matrix. Mathematically, a square matrix A is said to be an invertible matrix if there exists a square matrix B, such that A into B is equal to B into A is equal to the identity matrix. Now, let us derive one property of an invertible matrix. If A is an invertible matrix, then A into B is equal to an identity matrix. This implies determinant of A into determinant of B is equal to determinant of an identity matrix, which is equal to 1. This implies determinant of A is not equal to 0, or A is a non-singular matrix. This leads us to a result that if a square matrix A is invertible, then it is a non-singular matrix. The converse of this result also holds true. It says, if A is a non-singular matrix, then A is invertible, and A inverse is equal to adjoint of A divided by determinant of A. By Theorem 1, we know that A into adjoint of A is equal to adjoint of A into A, which is equal to determinant of A into the identity matrix. On dividing both the sides by determinant of A, we get the expression as shown. Now, comparing this expression with the expression A into B is equal to B into A is equal to I, we see that B is equal to adjoint of A divided by determinant of A. And as per the definition, B is the inverse of matrix A. So we have A inverse is equal to adjoint of A divided by determinant of A. Hence, A inverse can be calculated with the help of this formula, provided the determinant of A is not equal to 0. Meet Mr. John. He owns a stationery shop. On the eve of Children's Day, he displays stationery for students on a board. It shows that the cost of 1 pencil, 2 erasers and a sharpener is 13 rupees. The cost of 3 pencils, 1 eraser and 2 sharpeners is 19 rupees. Similarly, the cost of 2 pencils, 1 eraser and 1 sharpener is 12 rupees. The offer pulled in many students. Ryan was one of them. Being very intelligent and curious, Ryan thought of first calculating the cost of each article before purchasing them. So he begins by expressing the given information as a system of linear equations. Let the cost of a pencil, an eraser and a sharpener be X rupees, Y rupees and Z rupees respectively. Then, from the given data, the set of equations in 3 variables shown here can be obtained. Rearranging the equations in a matrix form, we get the equation as shown. Let's now learn to solve such systems of linear equations using the inverse of the coefficient matrix. Consider the system of linear equations in 3 variables as shown. In matrix form, this system of equations can be expressed as shown here. Let us denote the 3 by 3 matrix on the left-hand side by A, the column matrix on the left-hand side by X, and the column matrix on the right-hand side by B. So, equation 1 can be rewritten as A into X is equal to B. To solve this system, we have to find the values of the 3 variables X, Y and Z. In other words, we have to find the column matrix X. 2 cases arise while solving this equation. The first case is if the coefficient matrix A is non-singular. If A is a non-singular matrix, then A inverse exists. Multiply both the sides of the equation AX is equal to B by A inverse. We get the equation as shown. On simplifying, we get X is equal to A inverse B. This matrix equation provides a unique solution for the given system of equations, as the inverse of a matrix is unique. Such a method of solving a system of linear equations is known as the matrix method. The second case is when the coefficient matrix A is a singular matrix. In this case, the determinant of A is 0. Consider X is equal to A inverse into B. Now, A inverse is equal to adjoint of A divided by determinant of A. So we have X is equal to adjoint of A into B divided by determinant of A. While solving this equation, 2 cases arise again. That is, adjoint of A into B is either a 0 matrix or a non-zero matrix. If adjoint of A into B is a non-zero matrix, then the system of linear equations is inconsistent. In other words, the system of linear equations has no solution. On the other hand, if adjoint of A into B is a 0 matrix, then the system of linear equations is either consistent or inconsistent. Accordingly, the system of linear equations has either infinitely many solutions or no solutions at all. Let's now apply the matrix method to solve Ryan's problem. The arrangement of the given data in matrix form is as shown here. Let us denote the 3 by 3 matrix on the left-hand side by A, the column matrix on the left-hand side by X, and the column matrix on the right-hand side by B. So, we have AX is equal to B. This implies that X is equal to A inverse B. Hence, to find the cost of each article, we have to find the product of A inverse and B. Let's begin by finding A inverse. First, let us check if A inverse exists. First, we have to find the determinant of the given matrix. Determinant A is non-zero. This implies that A is a non-singular matrix. Hence, A inverse exists. Let's now calculate A inverse. Adjoint of A is obtained by finding the transpose of the matrix obtained by replacing the elements of matrix A by their corresponding cofactors, which is as shown. Now, A inverse is equal to adjoint of A divided by determinant of A. On evaluating A inverse, we get the matrix as shown. Finally, finding the product of the matrices A inverse and B, we get a column matrix with the elements 2, 3, and 5. This implies that X is equal to 2, Y is equal to 3, and Z is equal to 5. Hence the cost of a pencil, an eraser and a sharpener is 2 rupees, 3 rupees, and 5 rupees respectively. After calculating the cost of each article, Ryan feels quite happy. He bought some pencils, erasers and sharpeners and went home happily.